Buddy, trickling in here. So first, let's get this out of the way. Even though I work for AppDynamics, which is now part of Cisco, what I'm saying here is my personal opinion and my personal thoughts, and AppDynamics or Cisco does not endorse anything I say here. And even though I will be presenting things that we actually do there, I am presenting them as my own person here. So we all are kind of familiar with this triangulation. Software engineering is still this art form that hopefully delivers results that we can monetize. And we're always caught in this quandary where we have features that we want to ship. We have a schedule we want to ship them at, and we have a certain quality standard that we want to keep up. And in practice, we want all three, but really we can only realistically pick any two of them. So when we start our life as a startup, the schedule is everything, because the schedule is our burn rate. And if we can't deliver a product or something that's at least going to convince investors to give us more money, well, we're dead. So schedule and features, quality, well, we do our best we can, but basically get something out there that we can show our investors and hopefully find some customers. Once we have customers, well, the customers are all excited to use our product, but they find all these bugs, and they kind of come back and say, you know, if you want us to continue being your customer, you better do something about it. Meanwhile, of course, our business goes on, and we want to still implement all the features. And so we focus on features and quality, and inevitably, we start slipping. And we slip, but we still kind of sort of make it. But eventually, we find out and we get smarter, and we look around what other people do, and they do. Everybody talks about CICD, which is what we're kind of trying to do. And there, the hope is that if we focus on quality and schedule, just keep shipping, and keep making sure that we're always shippable. Well, features might come in or not, but hopefully the features will come in nicer that way. Basically, by reducing the stakes. Back when we were in this world, if you miss your release train and you have to wait another 3 months before you have a chance to publish your feature, there's an immense amount of pressure to get your feature done, and immense amount of pressure to delay to get the feature in, because otherwise you have to wait 3 months to get it out. The idea is in CICD, as we well know, that we want to ship all the time, so we reduce the pressure. If you miss this train, well, you'll release next week. What's the big deal? And hopefully we'll get closer to that triangulation. So what I want to talk about today is, though, I mean, how do choices that we make about how we deal with our built artifacts affect this whole triangulation? And I'm going to put this out here, and I'm probably going to get some, before you take out all the pitchforks and say that that semantic versions are actually pretty useful things, which they are. What I really mean to say is that if we prematurely apply our semantic versions to our artifacts, we're creating more problems for ourselves than we're solving. Because once you start using semantic version on artifact, you're assuming that things happen in a certain order, and that things get done on time, which is exactly what we're trying to relax when we do CICD. We're saying, we don't really care what gets done as long as we get something that works. And of course, dependency management becomes kind of tricky, because we keep having to update our POM files and say, okay, now we use version this of this thing, and now we use version that of this thing. Or we use dynamic versioning, and then we wonder why we can't reproduce our builds, because, well, whatever worked yesterday is now different. So what I want to talk about today is a way to avoid some of these quandaries. Here's an example of what the kind of trouble you get into when you try to use semantic versioning for your builds. And so you kind of like develop different features, and you set up your pipelines, and you deploy them to your various test environments, and you do all that. And well, if you do it this way, then you assume that there is an ordering. But what if feature B is done before feature A? Do you then renumber, or what do you do? So, I mean, if you work in the same organization, and if you are trying to all work together, forcing you to use these types of semantic versions is not really that productive. Compared to the time, I've got obviously my white hair here, so I remember the time when it was very cool to put SCCS ID at the top of every file you write, and then that gets put in at build time, and then it resolves into some serial number for your version of your file. We've kind of outgrown that nowadays, and we've accepted that putting serial numbers on file versions is not that productive. Instead, we use Git, or we use Mercurial, which decided to use content hashes instead. And we thereby reduce our dependency on centralized systems on ordering. We don't care when you do your commit and who does the commit where. We just care about the relative relationship between the commits, and then we merge all the time. I'm trying to explain how we can do the same thing with binary artifacts. So this is how I got started on the whole thing. There's a couple of little Git commands. Git helps us a lot to doing that. So the idea is really to use the content of your sources to figure out what your binary hashes will be. So one important command there is just to figure out what are the sources that are actually under Git control. This is a command that works. Lists all the files for a given Git ref. And this command has the feature it works also on a bare repo. Because one of the goals I would like to have is that this whole system that I'm building works server-side, so where we don't actually have Git checkouts. We just have our bare Git repos that sit there, and we want to pre-compute what would happen if we were to build something. So I have to make sure that all my Git commands that I use work on bare repos. This is really the interesting one. I don't actually have to go in and do SHA-1 computations of every file because Git has already done it all for me. Git works that way. And this is a command that actually will tell me what Git already computed for the content or the tree hash of any place within the Git repository. And this also works on a bare repo. So you can run this command, and if you know that you have one source directory that builds, say, a jar, just run this Git command on the root of that directory, and you get a content hash that includes all the files that are in that directory. And if that changes, well, then you have to rebuild, and if it doesn't change, you don't. So let's model a build. I mean, this is probably trivial in some ways, but helps to actually just remember that this is really what a build is. It's nothing really fancy. We take a bunch of source files, we do something to them, usually via Jenkins, and we then generate a bunch of derived files that hopefully represent our product and the thing we want to ship. We assume our source files are in the Git, and we assume that the source file also contains the build scripts that we use to build that thing, and that any third-party and outside dependencies are explicitly mentioned so that we don't use dynamic versioning, because if you use dynamic versioning, then you get different results depending on the time which you're in the build. So if you really insist on using dynamic versioning, we'll have to do some tweaks here to make this work. But for now, I'm not going to assume you don't. The derived files will always appear in well-defined locations in the file system. And for this system to work, we will want to not include any embedded dynamic version string or semantic version strings into those binaries, because the whole point is to not use the binaries for what we think will be the next release, but to keep reusing them later on if they don't change. So if you say, like, I'm going to build version 1.0 of the product, and I embed 1.0 someplace, and then if you click the About tab and it says 1.0, but that particular module doesn't change like for the next 10 releases, then it will still say 1.0 on the About tab, and that will not be so good. So you have to find a different solution for that particular problem. We select those derived files, and we publish them as a Maven artifact using the computed SHA-1 version as our version instead of the classic semantic version that we use. To make this all work like in practice, what I had to do, and you end up having to do that anyway, because you end up having to have a place where you list all the things that you want to ship anyway. So I might as well use that particular structure that I have to define regardless of what I do, and list all the files that my build will produce. And this is usually termed as a bill of materials. So what I devised here for our for our builds is a YAML format that essentially just defines all the artifacts that the build produce. It will show the locations, the locations where the builds come from. It will show me what Jenkins task builds those. And it will show me where the actual jar or whatever I built ends up when the build is done. There are various other use cases that you could use. For example, here, if you want to run a test, well, you run your tests and you declare that your JUnit XML files are your artifact, and then you can process them whichever way you want. Or if you want to do, a deploy, in that case, you care more about the side effect of the build, and the artifact will just be the log of what happened. But if it succeeds, well, then you have deployed something, and if it fails, you'll have an artifact that tells you or helps you at least debug what the problem was. So this is kind of a very generic definition of what a build is. It can be our normal definition of a build where we actually compile something and produce a jar. It can be a test run. It can be a deploy. It can be a combination of all those things. Now here's another little Git command, since we're into Git Arcana a little bit. Since this bill of material is an actual file in a version control, and we want to see the content, and when we're on the server side, we don't have a checkout to look at it, this is a command that will extract you from a bare repository the content of a file. Pretty sure this is not something revolutionary new here. But we need to do that if we want to actually do this, all these computations server side. We need to figure out what's in the bill of material for the particular commit that we're building. So the way we have set up Jenkins is relatively simple. We just use freestyle Jenkins projects. They have a single build step that runs a shell. That shell script first runs what I call our execute wrapper. That execute wrapper does all sorts of things that we expect any self-respecting build system that wants to maintain itself to do. It makes sure that the slave is in good shape to actually run the build. It makes sure that there's space available. And it will parse the bill of materials or retrieve whatever data it can from a server side that will have these informations already pre-parsed. So we know what the version of the artifact will be that we will be building here. And then it hands off control to the developer script. And the developer does whatever he wants in that script. And we expect that when it's done, the artifacts that got built are in the defined location on the bill of materials, and we take over the publishing. The reason we take over the publishing is because it's only our system that knows what the version will be. The developer is explicitly instructed to not think about that, because we don't want him to insert whatever he thinks the version of that thing will be. We decide that. So here's an example of a POM file that we generate that essentially demonstrate that principle. So you can see that there we have this is the actual version string that we computed. All these properties, you can insert them into your POM file, and they help you track back what the actual build was. For example, we get you can even go back to the actual build job definition. So if you look on the repository and you want to know what Jenkins job built that thing, you can look at the POM file and figure it out that way. This is all very cheap stuff to do, and I'm amazed that it's not done more often like that. But what about dependencies? Well, we'll get that. We'll get there. First, I want to talk a little bit about what we decided to call pipelines. This is not necessarily the definition that is widely in use. In fact, I had some trouble finding a real formal definition of what people call a pipeline. I mean, I think it's whatever the product makers that use pipelines decide what it is. So I follow that tradition and say, okay, I'm going to define a pipeline to be just a collection of builds that build something, and I consider them to be a group of things. That is, either they succeed altogether or they fail altogether. If one step fails, the whole thing fails. So in the classic build, test, deploy, I mean, that makes sense. If any of these steps fail, then we're not releasing. But you can use it for just about anything. So it's not, you don't have to hard code the fact that a pipeline always has to be a build, test, deploy cycle. the way we set up our pipelines on Jenkins is we have a special task that we call the launcher. And the launcher does all sorts of things. And kind of in the spirit of, I don't know if anybody was in the presentation yesterday where somebody described on how to make Jenkins do less or do less with Jenkins. I'm actually a full subscriber of that. And just like about 6 months ago, I managed to actually kick out the Git plugin completely for various reasons. So I'm no longer dependent on some of the idiosyncrasies of the Git plugin, so I can do all sorts of interesting things. But basically what the launcher does is check if has there been any change at all? Do I even need to bother to log? And yes, if there has been a change, then I will go ahead and look at the BOM and figure out what the SHA-1 version is, or if the server side already has them, I'll just retrieve them. And then for every build that's in my pipeline, I will check whether the artifact already exists on my Nexus or whatever repository, artifact repository you use. And if it's already there, then I don't have to build it, right? If it's present, I skip the build. If it's not there, I will obviously schedule the build. And if I have a build schedule, if there is a build schedule to do, if there's something to do, then I will set a build tag and then launch the actual indicator task. And so here we have this is actually a real screenshot of our Jenkins build log, and you can see that the launcher runs like every 15 minutes or so, and most of the time it notices that there's nothing to do, and every once in a while it notices that it did something, so it actually did a build and finished. So that's what the launcher does. This is kind of interesting. So this is all the things that the launcher does once it decides to actually make a build. I obviously put in a Git tag for every build I do. And I also have some tracking branches that I move along every time a build occurs. So the master pending build, for example, that's the build that's currently running. It's usually ahead of the current build. Current build is whatever build last finished, regardless of success or failure. The latest build, out of a curiosity of our history, is anything that had no build error but might have test errors. So it's like what you would usually see yellow or blue on Jenkins, but not red. And master stable build is the last build that was completely green, so or no test failures. So this would be a typical layout of those builds with some builds into probably some more commits in between. The reason why these branches and these tags exist will become clear in a moment. But let's go over what the indicator does. So the indicator is a kind of a variant of a multi-project job for which my partner here, that is hiding someplace here, Gangadhar, he wrote actually a nice plugin that does dynamic scheduling. We'll see that. We'll get into that a little bit later. But basically, this will actually run the tasks, monitor the results, and then set the pipeline status and move all those tracking branches around, depending on how the build fared. And the indicator jobs are all the indicator jobs for all the pipelines is what we then show on our Jenkins main page. And as the name says, it indicates the status of all our pipelines. This is what our dashboard looks like with all this in action. AppDynamics is a big product, and we produce lots of things. So on the horizontal, each row corresponds to either a group of builds of similar product components or just a single one if it's like a singleton. On the top, I have essentially time. You can see that by the dates at the bottom. And every one of these is a build number. And then you can see that some builds don't get launched. They just reuse the result of the previous build because whatever commit triggered those builds did not affect those builds, so they just get reused. Others get affected more often. You can see the status and stuff. You can go, this is actually an interactive UI, so you can actually go and expand, collapse those things to navigate it. You can also click on just about everything in here, and then you'll get the appropriate build report and links to the actual Jenkins build that run this. So this is kind of like a generic status dashboard that we use to indicate what our current build situation is. Oops. Click. So what we got so far, a map is a source set to a version string, which is SHA-1, which is computed from the contents. I can check that if a build using that source has been attempted. I can avoid rebuilding if it has already been attempted. I can even avoid rebuilding a failed build because, I mean, if none of the sources change, then why would it succeed this time when it failed last time? Yeah, that's the nice theory. In practice, there are sadly sufficient number of environmental reasons why builds can fail. Sometimes builds fail because, well, some third-party artifact server was down or something else failed. And so and some people just don't write very good build scripts, so they're not always very deterministic. And I mean, we are a large organization. I can't police every single build script that's out there. So we actually do retry failed builds because otherwise we have to somehow force to retry sometimes until we can slap the developers on the fingers and say, you got to really fix this. And we reuse older builds when nothing changed. Now there's even more. Now we get a little bit to see what all those branches and tags do for us. So we generate about 1 terabyte of artifacts per day per build. And with the advent of Docker and Docker containers and building Docker containers as artifacts, this is only going to get worse. So we just generate huge amounts of data. Our current artifact working set is about 12 terabytes. And we keep it that way and prevent it from growing to like humongous quantities by being very rigorous in how we discard things. So, but with the system we have now, it is relatively easy to figure out what we want to keep. Basically, we say everything that is not associated with a Git tag or a branch that points to that commit is something that can't really be referenced at any point. So there's no reason to keep it around. So basically what we do is when we essentially go and produce a whitelist of all the artifacts we want to keep by looking at what the SHA-1s were for everything that has a tag or a branch pointing to it. So if we go back and take a look at that, I mean, oops, where's that? This thing. So every commit that has a branch or a release, a non-build tag pointing at it, so every one of these has an associated set of hashes of all the artifacts that got produced by that build. So that creates me a whitelist. And I can then go ahead and go through my Artifactory or Nexus artifact repository, look at all the artifacts that are there, and everything that's not on my whitelist and is older than 2 days just gets deleted. And that works fine. We very rarely have a problem with something not getting resolved, and it's usually a consequence of some mistake or some bug someplace. So let's go back forward here. This is this. Since we are into Git ShowRef is actually a very nice command to know if you ever want to do a large-scale mapping of. So the use case is I want to know which tags and branches point to a given commit. Now you can ask that. I mean, everybody here probably knows git log -- decorate. That gives you like a nice output for every commit that tells you all the tags and branches that are pointing to it. But if you do it at scale, you'll find that it is very, very slow. Git is not optimized to give you that information easily. So git ShowRef just dumps you a list of all the symbolic refs mapped to the actual SHA-1s, and you then have to do the pivot operation where you essentially say, okay, which are all the symbolic refs that point to a given SHA-1. You have to do that yourself, but since you're processing the whole Git repository, that's not expensive. And so that's how we actually do our garbage collection. See how we're doing here. Okay. So releases are trivial. All we have to do is apply a Git tag, and then we are assured by the system that those artifacts will remain forever. And then we do whatever we want to do with the release. We just have to copy them, deploy them, or put them up for a download site or whatever. So why is this built avoidance thing so important? It's not just that we save time. I mean, the time saving is significant, but it's not the only reason. The other reason is that, I mean, we know that we all have like this pride in our build meister's job of making every build reproducible under any circumstances. But ask yourself honestly, how good are you at that? can you really reproduce a build that you built in the past? Do you really want to trust that? I mean, just imagine building, say, building a DMG file for a Mac OS version from 3 years ago. Do you think you can? Do you even have a build machine for that at this point? You might not. Do you have an image of that? Do you know? Can you retrieve that? Can you? I mean, good organizations will be able to do that, but not everybody can. It's much easier to just don't throw it away, you know, and just have it. The other thing is that if you spend a lot of time testing and a lot of time, I mean, you deliver an artifact to your QA team and they go and run user acceptance tests and they take like a week to then determine this is actually really good. And then you go ahead and throw it all away and rebuild from scratch, which is kind of what the Maven release plugin forces you to do. I mean, yeah, logically this should be okay, but I mean, if you get delivered a zip file that is not bitwise identical with what you've actually tested, I mean, you have to completely put your trust into the system that this will work. It's much nicer to just simply release what you tested, right? So that's what this system enables you to do. So what about dependencies? Well, let's go over that a little bit quickly because otherwise we run out of time. So in my bill of materials world, you just add a requires for other artifacts, and that artifact, of course, has to exist. So we add a definition for that gets built elsewhere. And the SHA-1 of the consumer of that dependency is simply the SHA-1 of the sources plus the SHA-1 of the consumed artifact. So that's very easy to do. Composite? Where do you see that? The composite, yes. It's me. I do a SHA of SHAs. So essentially I have a list of SHA-1s and I just run SHA-1 over that list of SHA-1s. I mean, I first sort it before you to make it. So you take a list. So you have a list of SHA-1s, you sort it, and then you just run a SHA-1 over the SHA-1. And that's cryptographically totally okay. And you still get something that's very, very, very unlikely to have a collision with something you've computed before. Where very unlikely means like not in this lifetime of the universe. So dependencies have several purposes. I mean, they define ordering and they allow you to reuse the artifact. They ensure that the artifacts that you depend on are available for you to use. So this is the mechanism that will allow you to actually make a build, test, deploy pipeline. You just simply say, okay, I built something, and then I have tests that depend on the builds, and then you just take the artifacts that I built and run them through whatever tests I want to do. And then if I have a deploy job, similar to the way I had it before, I just can retrieve the artifact I want to deploy and then run my deploy, produce the log artifact. So that's how dependencies can be used. So what the launcher just has to do one little extra step. It has to essentially check that if there's a dependency on an artifact that is not produced by the pipeline that I have to check that it's there because I have no way of producing it myself. And if it's not there, I can't launch, and that is usually an error. Or it's kind of expected. I mean, if I have a pipeline that tries to use that depends, say, on the results of another pipeline, then I can say, okay, well, the previous pipeline failed, so I don't get to run my thing. The indicator can do a couple of things. Well, first, it'll obviously figure out the right order in which to run those Jenkins jobs. But if, like, a prerequisite job failed, I don't even need to launch the downstream job anymore. Because, I mean, I know it's not going to succeed because the artifact isn't there, right? So I can do this little optimization there and at least fail faster than I used to. So that's basically the pseudocode that we developed in our indicator project plugin that we wrote to actually schedule all these jobs. It's very interesting that I really researched a lot about all the pipeline plugins that exist. I did not find one that did this type of scheduling, where essentially I have jobs and I have a dependency graph. And once all the prerequisites for specific jobs have completed building, it launches the next step. All I ever see is like phases, and everything within the phase runs in parallel, but everything in the one phase has to finish first, and then I can start the next phase. That's not what I need here, because if you scale that up to, say, 200 jobs, you'll find very quickly that it doesn't behave very well. So basically, that's the algorithm I wish that there was a plugin for, but I couldn't find one, so we wrote one. Oops. So here's an example run. That's kind of so it had three jobs to do, and it found two that didn't have any dependencies, and it ran those, and then the final one, the validate, which depends on the previous two, runs last, and then it gets done. And this here is what it looks like in practice. This is actually one of our production builds. This is basically our main build pipeline, and this is kind of a Gantt chart that shows you how all the builds get run and how long they take, and that downstream builds have to wait until upstream builds finish. So there are several examples. Here's, for example, one that failed due to flakiness and then got retried. And here we have a base lib that gets built, and then once the base lib is done, we have a bunch of consumers that got built. This is the typical pattern you see when we have tests. A huge number of tests get run on parallel once the thing that is being tested got built. And then we have some final aggregation and validation stuff going on. So this stuff actually works, and it's used, and it has been used at AppDynamics for a few years now. So, questions? Yes?
I have a question about building libraries. So do you have a tight coupling between your libraries and the application such that every time you rev the application, it will use the latest SHA from that library?
Short answer. So the question is, do we have a tight coupling between the library and the application? And the answer up to about 6 months ago was a clear yes. We essentially ran out of a monorepo, so the expectation was that any change you make affects everything. That's a trade-off. I mean, you have the debuggability, that is, you can actually run a debugger and look at every piece of code that could possibly be affected. But of course, you have the problem that, yes, indeed, if you change a piece of shared code, you essentially will break everything downstream of it. But on the counterpoint, you also had that feedback. Yes, what you just did was bad. And you notice it right there, instead of noticing it like whenever some downstream person decides, oh, I'm going to upgrade my dependency to use that, and then only then do you figure out that the change that you made broke it. So it's a trade-off. And yes, up until recently, that is the trade-off we took. Yes?
Would your approach work also for OSGI artifacts?
Say again?
Does your approach work also for OSGI artifacts, where the semantic versioning is a very important concept used at
OSI artifact?
OSGI.
OSGI. I'm not familiar with that particular concept. So if you are in a world where you have to use semantic versioning, well, we'll have. I mean, the answer seems to be no. But we haven't run into that. I mean, I wanted to make sure I'm not saying that semantic versioning is bad. It just has a specific use case, and that use case is when you have to talk to third parties with which you do not have a tight relationship with, or you choose not to have a tight relationship with. That can be within the company. I mean, if you want, you can treat every department in your company as a third party, or every development group as a third party. And that has a certain trade-offs that some people think are good or bad, but it's not necessarily a choice you have to make. You have a choice that you can actually be tightly coupled. So that's basically what I'm saying here is that. Yeah.
So how do you know what features you ship?
Say again?
How do you know what you ship? How does product know?
Well, when the tests, I mean, that still is the same old, same old. I mean, when we test the things we built, and once the tests pass, we ship it. So the nice thing about this is that since your test code lives in the same repository as all the other code. So the tests that you run, they use the same git commit that were initially used to build. So you know which artifacts there are. And then you just drop a tag, and then you can figure out what the artifacts are from there. Yeah.
But if I'm product, how do I know if my feature is shipped?
Well, you look at the changelog. Say again?
The changelog is in a ticket system. Or
It's in Git. These are issues that you have. They're somewhat orthogonal how to match. So we match. Obviously, we do like what pretty much everybody else does, is that we enforce that people put Jira references in Git commits, and we track the changes in Git. And whenever something gets merged into Git, Jira gets like a little link that says, okay, this has been merged, and then we get another link that when the build happens that says, oh, here's the build that actually contains that thing. And when we release, we even add a third link that says, oh, by the way, this thing has now been released in such and such. So we have all sorts of mechanisms, but that's kind of orthogonal to this problem. You would have a system like that even if you use a classic semantic versioning or separated project setup, right? Figuring out what gets used where. In some ways, if you have a monorepo, it's simpler because you know that it's whatever commits that were not in the previous release but are now in the current release, all of these get included everywhere. Whereas if you have like a distributed system, it might be more complex. Because if somebody adds a feature to a shared library, but not all your consumers choose to upgrade, then whatever that person did may appear in this little subproduct, but may not appear in some other subproduct. So you have a more complicated problem there. So in this, yeah, go ahead. We use Nexus for no particular reason. I guess it was just there when I got in, and there's no reason to change. Obviously in this system, all the indexing or dynamic versioning features that are provided by Maven type repositories are not very useful, so we don't use them. We just simply always use the direct retrieve the known version that we want. So it doesn't really matter what you use. We could have used a flat file system for that matter. Yeah.
Do you have any rules or rule of thumb for relationship between the number of repositories and the number of repositories inside a certain artifact, or how many artifacts per repository?
We started out with a monorepo. That means we just had one repository, which was big, which had its own issues. And all the artifacts got built from one repository. The trade-off is, as I explained before, is that you have then tight coupling. That is, any change you make immediately affects everything. So you get the feedback that you broke something by that change. But getting that feedback can be expensive because you have to rebuild everything that consumes you. So often people make a different trade-off where they say, okay, well, we'll have separate repositories for each jar or for each library, and we treat them each as an independent releasable item. And and everybody who consumes this treats that particular build as a third-party build. That is a different approach. And obviously in that situation, this method that I use here is not going to be that useful for you.
So the number of repositories is 1 to
yeah.
somewhere from 1 to the number of artifacts.
Yes, that's something like that. So this method favors large repositories that produce many artifacts. That's what it favors. It's very easy to the examples I've shown here were obviously one repository that produced all artifacts. It's easy to conceive of looking at multiple repositories, doing those hash computations, and then by essentially concatenating all of the bill of materials and just running the operations on all the machines and then figuring out what the things are. So the launcher would have to look at all the repositories involved, but that's kind of a relatively easy extension of the system. But of course, if you go all the way down and say, I actually do not want the tight coupling, I do want the separation, and I want to give every team the choice to say, I don't want to depend on the latest build of this other guy, then you wouldn't use this system. Yes?
So one of the steps that I often see in a pipeline, and I run into this repeatedly in different teams, is something like a node or a Python package, create new environment, blank workspace, generate or run the built-in package manager to regenerate all that.
Mm-hmm.
And that always
Well, that's not specifically. So the question is, so a common pattern is that, for example, for lots of interpreted scripts like Python, is that they use. I hear like virtual. What I'm hearing is virtual env. Is that what you're kind of referring to?
Sure.
I mean, the fact is that every build has to essentially first construct the proper Python environment before you can actually start assembling your module or your Python package, the Python package that you actually want to test and export. And the reason you do that is mainly so that you can, is mainly because of dependency management, because you are essentially saying, if you didn't do, or let's put it this way, if you didn't do that, then you would have to provide all the possible versions that you might have ever used in the whole lifetime of the product someplace. And then you are stuck with manipulating paths, or you have to produce, or if you want to do it the modern way, you'd have separate Docker images that each have the right version of Python with the right libraries installed, and then you can fire that up and do that. All these operations are kind of similar in some ways. They all end up having similar costs at virtual env. But the reason that people do that is you want to still, even though at this point in time you're using, say, Python 2.7.14 or something like that, but 2 years ago you used Python 2.7.10, and that might have had a different set of libraries. So if you then have to go back and patch something from a release you did 2 years ago, then you have to somehow recreate that environment. So in order to make that easy, that's why people do it that way. So I would actually not recommend trying to optimize that. I think they're doing the right thing. Yeah. Anybody else? Okay. Well, thank you.